We now begin looking at other uses of the definite integral. So far, we've used the definite integral to find area, net area versus total area. But there are many other things that the definite integral can be used. And today we're going to look at the concept of the average value of a function, right? So take a look at this plot. Right, so I'm going to plot some ordered pairs. Let's say they're like this, and let's say this x1 corresponds to y1, x2 corresponds to y2, and so on, dot, dot, dot. And then let's say this is x sub n, and that corresponds to y sub n, right? So we have n data points, and if we know all the y values, and I asked you what is the average of these n y values, so the average of y1, y2, dot, 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 yn. Well, if you think about it, how do we find the average of a set of numbers, right? If we have a discrete or distinct set of numbers, n numbers, the way you find the average is you sum them up. So let's say k going from 1 to n of y sub k, so that's the sum, and then just divide by however many of them, so n of them. And this is the average. Now, there are different notations that are used to represent the average. A pretty common one is the variable that you're averaging, and then you put a bar on top, right? Now, this is not the same kind of bar that we use when we're indicating the special x value that's chosen in a Riemann sum. This means an arithmetic average, where you take a sum and divide by the number of terms, right? So that's a pretty easy calculation, and you do this all the time, when you're computing an average. But now, suppose, well, in fact, let me do this. Let me draw something similar, right? But it's going to have a very important difference about it. So let's say this is my x1, and I'm just going to call it A. And then this is my xn, and I'm going to call it B. So I have those two data points there. But now, instead of having just isolated or distinct ordered pairs, what if I had a continuous function that essentially connected all those dots now? And again, every ordered pair on this graph has a corresponding y value, right? So the question now is, what is the average y value of the ordered pairs on this graph, right? So what is the average y value, right, of all ordered pairs on the graph? Right, so again, let's say I know the equation now, y equals f of x, and somehow I want to average all of these y values. Well, the thing is, the summation approach won't work because there are infinitely many y values. I can't list them the way I did here. I can't list the y values that are on the graph of a particular function. But it seems like the question of finding the average is an important one. So we need a procedure of how to do it. Well, it turns out we're going to take Mr. Riemann's approach, and so for instance, on that graph, or on this graph, what I'm going to do is pick some, again, distinct ordered pairs like this, similar to what I have up here, and start with an approximation of it to say, okay, I'm just going to average the y values of the blue ordered pairs that I have indicated here, right? And I know how to do those because these are distinct points, and I can use this as my approach. And then the idea is, what if we fill in more and more points? All right, so before I fill it in completely, let's see what the approximate average will be, right? So the idea is just like a typical Riemann sum, you break up the interval, right? And you have all these different x values, and then from each subinterval you pick one of the x values, and it could be, again, left, right, midpoint, or actually just a random choice from each interval, right? As long as your function is well behaved, and this is where continuity is going to come in, but as long as your function is well behaved, then you can show that all those Riemann sums, as you increase the number of points that you're using, or better yet, as we make our delta smaller, right, all those Riemann sums will get closer and closer. They will converge to the true average value. Okay, so let's write down what the approximate value is, right? So again, all I'm going to do is I'm just going to highlight one of them. So let's say we take the this as like my x. Now I'm not going to use the bar like I did before, because I don't want to use the bar to represent two different things. So I'm going to still use my x sub k, but let's just use like an asterisk to say I'm going to choose that x value, and then I'm going to plug it in here, and then that will give me the y. That's how I would find the y value. So it's going to be the special x value that I've chosen, whether it's the left, the right, or the midpoint, plug it into my function, and use that as my function value, right? And then I repeat that for each of the intervals here, right? So the let me go ahead and switch back to white. So the average value, right, is now approximately equal. Well, what would we do? Well, we would sum up all of these like we did over here and divide by however many, right? So if my partition is using 10 subintervals, then I would divide by 10. If it's using 100 subintervals, then I'll divide by 100. So the average is, so it's going to be this. So k going from 1 to n, and then I'll have my function values. So I'm only summing up the function values now, right? So at this moment, I don't see anything about delta, right? But don't worry, the delta is going to get there. And then this is divided by n, right? Speaking of delta, this is how we're going to essentially change this to make it look like an actual Riemann sum. See, a Riemann sum doesn't have this divided by n thing. But let's do a little trick or some algebraic manipulations to rewrite this division by n, right? So we know this, since our delta x by definition is the upper limit minus the lower limit divided by however many subintervals, I can write it like this, right? And then, so if I wanted to get rid of the n out of this expression, what I could do is I could realize that, so let's solve this equation for n, right? So that means my n times delta x over, well, actually, let me do it this way. Let's get this off. Right, so we have this. And then that means n is equal to b minus a over delta x, right? So now what I can do is I can replace what's here in the denominator. But if you look at it, let me write this expression in one other way. Dividing by n is the same as multiplying by its reciprocal. So I can have it as 1 over n there in front. That's like my constant. And then I still have my summation there. So k going from 1 to n. And then I have my function values like that, right? And then, yeah, so take what I have for n over here and replace this. So just a substitution, right? So it seems, again, it seems like I'm making the expression a little bit more complicated, but for a good reason. So put that there for n, and then I still have my summation. All right. Now, 1 over b over delta x just means that it's the reciprocal of this. So if I flip this over, the delta x goes on top, the b minus a in the bottom. So I have now delta x over b minus a, and then here is my summation. All right. And now, because the delta is a constant, and remember this when we were doing our Riemann sums, that there were times when it was convenient for us to factor out the delta and put it outside of the summation. Well, the same way we can factor it out, we can distribute it across the sum, right? So what I'm going to do, since the delta x is a constant, I'm going to distribute it across the sum. And that leaves 1 over b minus a in front of the sigma. And then take the delta and multiply the function values. So like this, delta x. And now, isn't that our Riemann sum? Right? And remember, look at where we started. We just started with the same formula for an arithmetic average. You take the sum of the terms, and what are we summing up? Well, we're summing up these discrete function values, those blue ordered pairs on my graph, right? So we're summing up the y values, dividing by how many of them, that's the average. But we've shown that this average can be expressed as a Riemann sum. And then now, if we want, remember all of this is just an approximation to the average value. To get the true average value, we let our delta get very, very small. What happens when delta gets very, very small? Those blue dots, you have more and more of them, and they get squished together. They get squished together until they start filling in all the gaps, right? All the gaps, and you can't tell where one starts and the other ends, and what you end up with is this blue continuum like this, right? So then we would get all the y values on the graph of this function, and we would be computing the average of all of them, right? But we know what happens to a Riemann sum as we let delta approach 0, right? So let's write that down. So to get the exact, not the approximation now, the exact average value of y equals f of x, again, over the interval a to b, right? That's where we started. So over the interval a to b, we let or delta x approach 0. How do we do that? By a limit. So here is the, so therefore, the y-average now is exactly equal to the limit of this. Now, this 1 over b minus a is also a constant, so I can write it like this. So it's that constant times the limit. This is one of our limit properties from Calc 1. So the limit as delta approaches 0 of my summation, your special x value there in your Riemann sum, and we know that this turns into a definite integral, right? So the average value of this function is 1 over b minus a, and here's the definite integral. We know that the limit of the sigmas, that gets replaced by our integral sign. The lower limit here is where the graph of the function would start, which is at x equals a, and then the upper limit where it ends. And then we know that the f at these discrete points turns into the continuous f, and our delta x converts into dx. And this is our formula for the average value of a continuous function. We have to use continuity there over the interval a to b, right? So this is our definition for average value. And it looks, I mean, it doesn't look much different from the formula for our net area. The net area is right here, right? And it's like we're just multiplying it by this constant. So in a sense, you know, the average value could be described this way. It's 1 over the interval times the net area, right, of the region bounded by y equals f of x, right? Because again, we know that this is just a regular definite integral. What's new is this 1 over b minus a, all right? Okay, so let's do a couple examples of this, and we'll see how it goes. All right. So what I'm going to do is just state the function, state the interval, and then mention that we're finding the average value. So let's say our function is something simple like x squared plus 2x, and let's say the interval is from x equals 0 to x equals 2, right? If you were to graph this, right, so this is a parabola. It has roots at x equals -2, and then also at x equals 0, and then, but from 0 to 2, it basically looks like that. Well, actually, that's terrible. It looks more like that, right? Because at 0, it's at your y value is 0, so it passes through the origin, and then it's this part of the parabola right there. So essentially what we're going to be computing now is finding the average of all the y values of the ordered pairs on this function's graph from x equals 0 to x equals 2, right? The computation itself is relatively simple, but it's making sure that we understand the concept behind what we're doing. So this is a notation that we've used. Another notation is this: sometimes you use the y and then you use AVG as a subscript, which is an abbreviation for average. So either one of these is acceptable, right? And let's use our formula. In fact, let me pull it down so you can see the formula right there. So it's 1 over b, which in this case is 2. Let me not rewrite the formula since it's already there. So it's 1 over 2 minus 0 times the integral from 0 to 2 of whatever my function is. And here my function is in terms of x. So this is x squared plus 2x dx. All right. Well, let's see what this number comes out to be. So this is 1/2. And then our antiderivative, so now we have to evaluate this using our fundamental theorem, find our antiderivative, which is 1/3 x cubed plus x squared, and then I'm going to evaluate that at 0 and at 2, and then take a difference. So I have to have that 1/2 there. When I plug in the upper limit, what do we get? We get 8/3 plus 4. 2 squared is 4. And then at the lower limit, this entire polynomial evaluates to 0. So it's 0 plus 0, right? So that works out nicely. So let's simplify. This is, so 8/3 plus 4, you can write 4 as 12/3. So 8 plus 12, that's 20 over 3. So you have 1/2 times 20 over 3, and then that's 10 over 3, right? So that's our average value. Well, what does this mean with respect to the graph? Well, okay, so let's see. So we know that on the interval 0 to 2, this function it starts at 0, and then when x is equal to 2, let's see what the y value would be. It's going to be 4 plus another 4, that's 8. If you draw the graph of the average, right, the average just comes out to be this constant. So if I were to graph the average, it would be a horizontal line because it's a constant, and the y value would be at 10/3. Now 10/3, it's like that's 3 1/3, so it's not even quite halfway there. So basically, if I were to draw this, right, this would be the line y equal. In fact, let me write it as the average would be y equals 10/3, right? So again, it's saying you have some y values here that are below the average. You have some y values here that are above the average. But if you average every y value on this graph, right, when x goes from 0 to 2, they all average out to 10/3, right? Right? And the reason why I wanted to do the graph is because there is a follow-up question that can be asked, and I'll do that with our second example. But I just wanted you to see the white graph. That's the graph of y equals x squared plus 2x. That's that portion of the parabola. Now that we've computed its average value to be 10/3, because it's a constant, its graph will be that horizontal line, right? In the next example, we're going to see at what point does a function equal its average. So now another important question is right here. What's the x value that when I plug it into the function, I will get the exact average of 10/3, right? Let's do another example. So you'll see another example of the average value calculation, and that example will answer that second question, right? So let's scroll down here. Let's look at number 2. So let's say something like the square root of x, right? So now this is our square root function, and let's say x is now between 1 and 4, right? So part A, find y bar, right? The average value. Okay, well let's set it up. We have our f of x, we have our a, we have our b. We now know the formula for the average value of a continuous function. So it's 1 over b minus a times the integral from a to b of my function. And as soon as I see the root, I know I need to rewrite it as a power, and that power is 1/2, right? So we have 1/3, and then using the power rule, so add 1 to the power becomes 3/2. Dividing by 3/2 is the same as multiplying by 2/3, right? And then I have x to the 3/2. And then this is evaluated at 1 and at 4, right? Now, the constant in front, we can simplify this product. It's 2/9. And then let's apply the second version of our FTC. So evaluate the antiderivative at x equals 4. If you plug 4 in, 4 to the 3/2, that's 8. And then 1 to the 3/2 is 1, so we have this. And then, so what's this? 7 times 2, 14/9 is the average value, right? Well, let's do the same thing that I did before. Let's sketch the graph of the square root function. Now, the square root function, it starts at the origin and then it goes up. But here the interval goes from 1 to 4. So what I'm going to do is I'm just going to sketch the portion of the square root function. When x is equal to 1, it has a y value of 1, so it starts there. And then when x is equal to 4, it has a y value of 2. So we're there. And then, and we know the basic shape of a square root function. It's kind of like that, right? So that's our curve. And the average that we found here is 1 4/9. So that's just a little bit less than 1.5. So it's not quite here. So let's graph the average. So it's roughly here. And if we graph it, right, so this is the average value of 14/9, right? So again, if you average all the y values on this portion of the square root function, and again, there are infinitely many of them, so we can't use a regular summation, right? The integral is what does this sort of infinite summation for us. It sums up all the function values here, right? And produces this average. So now let's look at part B of the question that is asking at what value of x is this function equal to its average value. So at what value of x does my red graph intersect with my white graph? So the question might be worded like this. Find all, and you say all because it might be more than one depending on the function. So find all values of x in our interval where our function is equal to its average. Right? Well, that's now the calculus part of this is done. The calculus is done in order to compute the average, but this is basically saying, again, let me even put it here, and well, and here is the function, the square root of x. So when you think of it graphically, you have these two functions. One is non-linear, the other one is a linear, specifically a horizontal line, but you're trying to find the value at which they intersect. How do you find, where two functions intersect? Well, algebraically, it means that the square root of x would have to be set equal to 14/9 and solving for x, right? So, because again, when you look at the wording of the question, it's telling you what to do. The function is equal to its average. So set f of x equal to the average value and solve for x. Right? I mean, it's all in the wording, right? So take your square root of x, set it equal to 14 over 9, and this is a simple equation to solve. Square both sides, so then your x is the quantity 14 over 9 squared, which is 196 over 81, right? So I think my sketch is a little bit off here, and that's not surprising. I'm not a really good sketcher, because this is a little bit more than 2, so it really should be over here. And I can see where, yeah, my horizontal line started to dip a little bit. But basically, if you were to plug this x value into the square root function, then you're going to get the average value out, right? For different values of x, some of the y values are less than the average, so that's this portion of the graph. Some of the y values are bigger than the average, that's this portion of the graph. What we just found is the exact point at which the average is equal to the function, or vice versa. The function is equal to its average. All right? So average value, a straightforward concept, but it's the first of several different uses of the definite integral that we're going to be looking at. And I know you're probably really excited to see the next one and the one after that, and so on and so on. So see you in the next video.